The estimators need to be derived using the method of estimation, namely ordinary least square, and then we call for the definite properties, and thereby we are ready to go for the inferential modeling. As we get into the first important issue of method of least squares, we have discussed about a two-variable regression model. So a two-variable regression model comprises of a dependent variable y, and there are two terms, which is beta 0 and beta 1, and accordingly we are estimating it using the method of least squares, that is by minimizing the sum of errors. So in this particular discussion, we see that the error term ui hat, which is basically the difference between the actual value and the predicted value, and thereby we sum of square of that, and by substituting the above expression of beta 1 to beta 2 xi, we get the normal equations, and after solving them or after differentiation, we get the estimated values of beta 1 and beta 2. So this calls for the OLS, which means ordinary least square. The normal equations are derived, and accordingly beta 1 and beta 2 are already derived as done in the previous module. Now we get into the very important part of this estimation procedure before we jump on to the properties. We need to address the issue of importance of normality of these assumptions. Why the normality assumption is very much required in this entire process. So for the normality assumptions, we go for CNLR, which is classical linear regression model, and in this particular model, we say that the error term is normally distributed. What do we mean by that? That is, on average, the error term will have 50% of the observations on the right hand side and 50% of the observations of the left hand side of the distribution. This also calls for the mean, which says that it has a zero mean, which means on average the value of the mean will be 0. The variance has to be constant, otherwise if the variance differs, then the estimation will be biased. And most of importantly, the covariance between the errors must be 0. So this is actually being done by a normally distributed variables, where we call for zero correlation between the error terms and also constant variance and zero mean assumption. Thereby we go for the importance of the normality assumptions. As we can see that the very first important assumption says that the distribution of sum of a large number of independent and identically distributed variables tends to a normal distribution as number of variables increase indefinitely. This means with the increase in the number of observations, we can say that on average it will follow a bell-shaped distribution. Secondly, we can see that if the number of observations is not very large, then the estimated procedure will not be robust and the inferences cannot be drawn accordingly. Thirdly, we can see that the OLS estimates has to be given a proper inference. That is very important in the estimation procedure. And finally, we can see that the distribution will have two parameters whose mean and variance needs to be computed. So as we go on to the normality assumption, we also need to trace on the relevance of the OLS assumptions, why they are needed. Because the objective of the researcher is not only to estimate the model, but also to draw the accurate inferences. So for proper inference, for proper drawing the conclusions and the policy prescriptions in future, the estimation process has to be robust, and that depends upon the existence of the OLS assumptions. Secondly, we can see that when we are collecting the data from the population, it is subject to sampling error. So how can this sampling error be minimized? That also should be stated in the OLS assumptions. Thirdly, we can say that all these distributions suffers from a specification problem. So to avoid some specification problem, we need to have to stress on the OLS part, and thereby the assumptions come up. And also this calls for the assumptions for some explanatory variables which may be correlated with each other. So basically the relevance of the OLS assumptions is very much important, mainly for drawing the inferences after the estimation process is being done. So thereby we go for the Gaussian standard CLRM, which stands for Classical Linear Regression Model. So in this CLRM, we start with the assumptions one after the other, as it is said that it is linear in the parameters, as it is already explained that the error should not follow any systematic pattern, and on average it should have a zero mean. Secondly, the variables are non-correlated and not random. This also important says that they should not be related with any kind of error term. If it is found, then endogeneity will be a problem. Next, we have the conditional mean should be 0. That means whenever I am taking the error term, given the value of the independent variable, on average it must be 0. And that is what we see the conditional mean, and this is very important and similar to zero mean error or zero mean assumption. Next, we have the assumption of constant variance, which means that over the sample, the variability should be same. This also goes for zero autocorrelation. Among the time periods, it should also have the zero correlation, otherwise error should be dependent and that will be reflected in the estimated residuals. There should be also taking care of the degrees of freedom, because if it is lost, then the estimated value of the slope coefficient will become less and the null hypothesis will be always accepted. Also, there should not be any identical values in the distribution or the repeated values in the distribution, and more importantly, outliers must be taken care of. So outliers, we mean large observations or any extreme observations. So if there is any extreme observation in a data set, then definitely it will distort the result. For example, when we collect the data from an income group and we do not categorize, then in the data set we may have high income as well as mixed up with the low or the medium income. So any kind of estimation procedure will fail because of the presence of strong outliers. So this should be taken care of. And thereby we can see that the OLS assumptions will be very important. Now we go for the properties of OLS regression estimates. By property 1, we mean linear. By property 2, we mean unbiasedness. And property 3 means best minimum variance. When we call for the property, we have to categorize into small sample and large sample properties. By the small sample properties, we mean that the property 1 of linearity. So when we talk about linearity, it means that the model must be linear in the parameters, as it has been already stated in the OLS assumptions. Unbiasedness is very important property because when we are collecting the data from the population and we are getting the sample data, on average, it must be equal to the representation of the population. Because we should always remember that the beta, which is basically a population parameter, is being proxied by the sample statistic, which is beta hat. So actually, when we want to talk about the property of unbiasedness, then the mean of all the beta hats must be equal to the beta. And since it follows a random distribution, since it is also correlated with the error term, we need to find out the expectation of this beta. So basically, it is coming out from a random variable. We take the mean, and that is the expectation of the beta, which means that expectation of the sample statistic beta hat, that should be equal to the beta, and that is how the biasness can be removed. So actually, a good estimator should be unbiased. And moreover, the variability should be constant. So whenever we consider the variability constant in the OLS assumptions, here we basically derive the concept of a minimum variance. So basically in this particular three properties, as we can see, that if the estimator is unbiased but does not have the least variance, this does not attribute to the base property. It may happen that under any kind of assumptions, the estimator happens to be unbiased, but it is not satisfying the property of minimum variance. Then we cannot say it is a best variance property or it is an efficient estimator. So actually, if the estimator has the least variance but is biased, then also it is not satisfying the criteria. In some of the models, we will find out that it is having the property of minimum variance, but it is biased in its nature, as if the true population parameter is more or less sticking to the sample statistic. So this makes it to be violating the property of base property. So for a base property, it should satisfy two properties together. One is the unbiasedness, another is the minimum variance together. And this actually comprises of the small sample properties. Apart from that, we have two other properties which goes for property 4 and 5, asymptotic unbiasedness and consistency. That means, as we know, that if we increase the number of observations, then the sampling error comes down. That is, the sampling error is on the fall. So this actually goes for asymptotic unbiasedness, and as a result of that, sample statistic will be equal to the population parameter. Moreover, when we call for consistency, it also says that if I increase n to infinite, then the variance will come to 0. That means it is reducing the variance with a large increase in the observations. So basically, we are having the 5 properties as the best properties of estimators. First 3 are considered in the small sample property, and the remaining 2 as the long run or in the large sample properties. So as we move on to the derivation of the blue property, this is basically referred as best linear unbiased estimator. So as we go for a 2-variable regression model and we go for a blue property, we have to be very careful about the slope coefficient. So the slope coefficient which we have derived in the last model or using the method of least squares, that has to satisfy the property of linearity, has to satisfy the property of unbiasedness, minimum variance, and then only we can say it is the best linear unbiased estimator. And that is how we go for the blue property of an estimator. So when we go for the blue property of an estimator, we start with the first 2 cases, that is the property of linearity and unbiasedness. As we go back to the property of the linearity, we can see that this beta 2 hat which was already derived under the OLS comes out to be summation xi yi divided by summation xi square. If we remember correctly, xi is the deviation of capital Xi from its respective mean x bar. So small xi is basically capital Xi minus x bar. Similarly, small yi is basically capital Yi minus y bar. And in the denominator, we have summation of xi square, which is capital Xi minus x bar whole square. So if we come on to the next step, we can see that the beta 2 hat is written in the small letters and it is written summation of small xi, and instead of capital Xi, we are writing small xi and we are writing capital Yi by summation of xi square. So when we go for this kind of derivation, we can see that summation xi yi, where this capital Yi is being written as yi minus y bar. So why are we doing this? We want to show that in the numerator, how this small yi gets converted to capital Yi. So for that reason, we are doing this derivation. So to show the derivation, we start with small yi. We actually write down small yi properly, which is capital Yi minus y bar. Now we remove the bracket. After removing the bracket, we get summation of xi capital Yi minus y taken outside the summation sign, and within the summation sign we take summation xi. This is just done from the previous step. After that, what we do, we keep the first part as it is, which is summation of xi capital Yi minus in the second part capital Y taken outside the summation sign as usual, but within the summation sign we take xi minus x bar. So from here we can see that any kind of value, if it is taken the deviation from its mean, then it will end up to 0. That means the second component does not exist at all. The second component does not exist at all. This is absolutely equal to 0. Only the first component retains, which is summation of small xi capital Yi, and that is being substituted in the numerator. So in the expression of the beta 2 hat, we have actually taken up the original expression as we derived in the OLS estimation. And after that, in place of small yi, we are writing the capital Yi, and we have shown the derivation in this way. Why this is done? Because this is required for proving the unbiased or minimum variance property that we will take up accordingly. Accordingly, we can see that this beta 2 hat can be written now summation xi, which is written in small letter because it is the deviation from the x bar, capital Yi, which we have derived just now, divided by the denominator summation of xi square. Now here we are assigning a weight in the sense which is ki. So this ki is basically a fraction of xi divided by summation of xi square, so that we can consider that it is as if k1x1 plus k2x2 plus k3x3, where I is running from 1 to n. So this is basically done to derive the linearity property of the beta 2 hat, which is the very basic property that beta 2 hat should be having. So in this particular process, we can see that estimated value of the linear estimator, because if we take up ki, and ki can take different values starting from k1, k2, k3 up to kn, and finally we can go for summation ki xi, which is basically coming up as a weight which is assigned to the estimated coefficient beta hat. At the same time, we can also have some features of this ki, because this ki is basically in the numerator we are having xi, and in the denominator we are having summation of xi square. So this ki summation of ki is 0, because we all know that in the numerator we have the xi minus x bar. So if we take the sum, then it comes up to be 0. Similarly, we want to show that ki square is basically the inverse of summation xi square. And finally, we can see that if I multiply with small xi or capital Xi, it will be 1. So any kind of weight, when it is taken, either the sum of the weight will be 0, that is over the sample, the observations must end up in 0, which also follows zero mean assumption of the error term. Also, summation of ki square will be dependent upon the xi, that makes the validity of this weight. And finally, when we go for summation xi, ki xi multiplied, they should be equal to 1, because that is how the sum of weights is equal to unity. Now, from the above expression of the beta 2 hat, we can now write in a proper manner summation of ki, which is basically the weight, into beta 1 plus beta 2 xi plus ui. This is nothing but the yi that we have taken at the basis of the model, because we want to show that it follows a system of linearity. Now, if we just take out the bracket, if we just remove the bracket and put the summation sign before ki, then we are getting, basically we are getting beta 1 summation ki plus beta 2 summation ki xi, which we have already said that it should be 1, and ki ui, which should be actually 0. Why 0? Because ki has to be non-stochastic. So this is one of the very relevant Euler's assumption that none of the explanatory variable, not the weight we are assigning, should be correlated with the error term. Otherwise, it will pose a problem of endogeneity, and that should be always avoided in this OLS process. So after this, what we get, beta 2 hat equals to beta 1, because we have shown summation ki is 1. So this ends up with only beta 1 plus summation of ki ui. What is this? This is basically coming up to be 0, because we know that summation of ki ui should not have any relationship. So when we go for taking the expectation on both the sides, why we want to take the expectation? Because this happens to be a random variable and we want to take the mean. So we want to take the mean of the slope coefficients, and after taking the mean, we end up as expectation of beta 2 hat, which is basically beta 2, which was basically the true representative of the population parameter. Because beta 2 hat is the sample statistic. On average, it should be equal to the population parameter plus summation of ki, which is already there, as because it is a weight, and expectation is introduced just before ui, because we are always after zero mean assumption of the error term. So we can see that expectation of ui boils down to 0. So it ends up with the final expression, which is expectation of beta 2 hat equals to beta, and it's mentioned that expectation of ui is 0. So we can see that beta 2 hat is an unbiased estimator of beta 2, because over the time frame, over the sample observations, beta 2 hat should not be influenced by the error term. So two properties are henceforth cleared. One is it is a linearity in parameter, because it is basically ki yi or ki xi. And secondly, when we are taking the expectation, it should be equal to the unbiasedness property of it. So that is how the unbiasedness property is very important in this discussion, because it refers to two properties together. One is the linearity and the unbiasedness, and this calls for minimum variance that comes up consecutively. Hence, after the discussions of the unbiasedness property and the linearity property of the estimator, we are ready to take up the property of minimum variance of an estimator, because this happens to be the best property of any estimator in this entire model. when we are analyzing any estimator properties, we should be clear about the linearity and unbiasedness, but moreover, an estimator can be best if it is considered to have the minimum variance. So for that, the minimum variance property takes care of. So for a minimum variance property, we start from the basic expression of variance of any random variable, say x. So if we go for a variance of a random variable x, which goes by the expectation of x minus the mean of x whole square. So in this case, we can refer to this particular expression of variance of beta 2 hat. Whenever we are referring to beta 2 hat, it is the estimated slope coefficient under the ordinary least square model already derived. So as we go for that, variance of beta 2 hat is equal to expectation of, because as if we can see that it is as if the variance of x happens to be a random variable. So beta 2 hat is the value of the slope coefficient as it is mentioned, minus expectation of beta 2 hat whole square. So this expectation of beta 2 hat is related to the mean that we have already computed whenever we have done the unbiasedness property. So from there we can see that expectation of beta 2 hat remains as it is minus beta 2. Why are we substituting this? Because we have just now proved that beta 2 is an unbiased estimator of beta 2. So beta 2 hat is an unbiased estimator, which means that the sample characteristic is basically the true reflection of the population parameter, and that we have proved, so we can easily substitute expectation of beta 2 hat equals to beta 2. Now beta 2 hat minus beta 2, which is basically equal to summation of ki ui, because in the last step of the unbiasedness property we have seen that beta 2 hat minus beta is actually given by the weight which is assigned as ki multiplied by the ui, and since it's a variance we have to square it off. So we have to square this entire expression of summation ki ui whole square. Now whenever we are squaring it up, then we have to take care of some own terms and some cross terms. So as we go by that, we put expectation outside the bracket and we are putting the k1 square u1 square, which is basically with the first observation as we are squaring up, and this runs for n times. So it is coming up as k1 square u1 square plus k2 square u2 square plus, and this continues dot dot plus kn square un square. So these are the own terms which are considered in this expression. After these own terms, we are getting the cross terms, which means 2k1 k2, because it is basically taking up the two values, u1 u2, and it continues to the last term which is n minus 1 and basically related to un minus 1 and un. So you have already seen that the error of the two observations should not be correlated. So this cross term should not be existing as per our OLS assumptions, and we should be more interested with the own terms, which is k1 square u1 square plus k2 square u2 square, and that continues to kn square un square. So in this particular variance expression, we see that beta 2 is treated as a random variable of variance x, and on the basis of the variance x, we can see that expectation of beta 2 hat minus expectation of beta whole square, and this gives rise to beta 2 hat minus beta, which boils down to summation of ki uy whole square, which was already derived in the last expression when we did the proof of unbiasedness. And from there, if we just expand this term, so after expansion, we get the own terms as well as the cross terms. So that is how the variance of beta 2 hat is stated in this particular step. Now we move on to the next step, where we see that expectation of uy square is sigma square as per the OLS assumption. So whenever we are moving to expectation of uy square sigma square, which means that the constant variance is one of the OLS assumptions which says that the homoscedasticity must prevail, and uy uj will be 0, which means two terms should not be correlated. Two error terms should not be correlated as per the assumption of non-autocorrelation. So keeping in mind that, we can write variance of beta 2 hat, which is given by sigma square summation of ki square. So what is this ki square? Ki square is basically the weight which was already assigned, And from the definition of the ki square, we can know that it is basically coming up as sigma square by summation xi square. So how this sigma square by summation xi square is coming up, that is basically discussed in the subsequent steps. So we start with the very basic step, which is beta 2 hat is summation of ki yi. This is already done in case of the estimated value of the coefficient, where ki is the weight, which is given by xi by summation xi square, and yi is substituted in the capital letter as it is seen, because this yi was basically taken up from small yi when we derived the property of unbiasedness. Now how to write this ki? Ki is basically written as xi minus x bar, because that is the original definition of ki, because xi in the numerator, which is in small xi, divided by summation of xi square, that also in the denominator, which is also in small letter. So on the basis of this, we have written like this. Now we have seen that beta 2 star or beta 2 hat, whatever we say as the predicted value, is having the property of linearity. So whenever they are having the property of linearity, they are basically linear in the parameters or linear in the variables, or they have to be absolutely linear in the parameters. So what we mean? We mean summation of wi yi. So when I say summation of wi yi, this wi is the weight which is being assigned, and this yi is considered to be the estimated value or the original observation yi. So whenever we are taking the expectation on both the sides, we write summation of wi as it is, but in case of yi, we put an expectation before, because yi is related with the error term as per our original model. So yi is basically random variable, so we take an expectation behind that. Now we can see summation of wi, and in place of yi, we substitute the two variable regression model, which comes out with beta 1 plus beta 2 xi, because this is basically coming up as the original model as stated in the equation. So after this, what we get, beta 1 summation wi, which is considered to be by removing the bracket, multiplying with the beta 1, and then we get beta 2 summation of wi xi. So what we are basically doing? We are basically arranging the expression of beta 2 hat, which has already been done. Then on the basis of the ki weight which is being done, we are basically writing in terms of wi yi. So this ki takes a new name of wi, and then we are taking expectation on both the sides in order to show that with the help of the expectation, how can we boil down to the expression of the variance. So on the basis of that, we can see that the summation of wi, which is 0, and summation of wi xi is 1. So why summation of wi 0? Because wi has xi in the numerator, small xi. So small xi means capital Xi minus x bar. So when we are taking the deviation of an observation from its mean, then the sum is equal to 0. So this boils down to summation of wi equals to 0. And secondly, wi xi 1, which is also basically the property of this weight, which is wi. So if I put that summation of wi 0, then the first component gets eliminated or gets removed, and we are ending up only with the second component, which is beta 2 summation of wi xi. So if we go for the next step, which says variance of beta 2 hat. So when we call for the variance of beta 2 hat, basically we are taking the variance of summation of wi yi. So since we have written beta 2 as summation of wi yi, we are taking the variance of this entire expression. And after that, we can see summation of wi square, because once we are taking the variance, and if we remove the variance and keep the summation sign, wi takes up a square form. And then we have the variance of yi, which takes up separately, because wi is after all a weight which takes up the square form, and it lies just outside variance of yi. Now we have already noted that variance of yi is equal to variance of uy equals to sigma square. Why this is being done? Because yi basically follows the constant variance which is reflected in the error term. So this is by the note or by the assumption of the OLS which says that it has a constant variance, and from there we go for sigma square summation of uy square. Why sigma square? Because we know that the summation of uy square is sigma square, which is already being done. So variance of yi is equal to uy square, which is sigma square as per the OLS assumption. So only summation of wy square comes in before the summation sign, and sigma square is taken out as the bracket. So this goes back to this statement already in this slide which says expectation of uy squared is sigma square. So from here we are mentioning the last step in this particular variance of beta 2 hat, which is sigma square summation of wy square. So basically this wy is basically the weight which square form we are taking, and accordingly we are doing the derivation and we are showing it. So this is carry forwarded from the unbiasedness property. Now let us expand this wy square. So what we get in the next step is equal to sigma square. Now this summation wi, what we have done, this wy square is basically written in this way just to take account of the two terms. These two terms are identically same, but for the purpose of the derivation we have written as minus xi by summation xi square plus xi by summation xi square, so that cancellation terms, if we just cancel them out, then it will eventually boil down to only summation of wy square. But why it is done? It is done to take care of the cross terms, and it is done to take an expression of the variance of beta 2 hat. So after this, as we go for summation of sigma square or sigma square come outside the bracket, summation within summation sign, then we have a bracket started where we get wy minus xi by summation of xi square, which is already taken up at the first component. And then we are basically decomposing into two components where we see plus sigma square summation of xi square by summation of xi square whole square, because in the denominator already it is summation of xi square. If I take the entire square term, then it will be added on. So it will be summation of xi square whole square, and it is just as if a plus b whole square where we have a square plus 2ab plus b square. So the cross term comes in, and this cross term is given by 2 sigma square, and we have a and b. So if we look at this derivation from the beginning, then wy minus xi by summation xi square, this is say small a, and xi by summation xi square, this is say small b, as if we are doing a plus b whole square, which boils down to a square plus b square plus 2ab. So if we refer to this expression, a square is the first term, which is sigma square, which is already there beside the summation sign. So a square means wy minus xi by summation xi square whole square. This is the a square. If we say this entire expression to be a, plus b square, which is the second term, which happens to be sigma square summation xi square by summation xi square whole square, and we have the cross term which is 2 sigma square. This 2 is appearing from the basic formula of a plus b whole square, which calls for a square plus b square plus 2ab. So this 2ab component is basically 2 sigma square summation of AB written separately. So that is how this decomposition is being done. So in this decomposition, we are following the simple formula of A plus B whole square. So after this, what are we getting? We are getting sigma square summation of WY minus XI by summation XI square whole square as the first component. And in the second component actually retains, which is sigma square, where the summation of xi square and xi square whole square, it is cancelled out. So only one component remains. And this component is 0 because wyxi from the very beginning it is 1, and there is no relation of the two error terms in the two periods, because we are constantly stressing on the OLS assumptions that errors may not be or should not be correlated with each other. So if we can write this as wy is xi by xi square, then variance of beta 2 hat comes up as sigma square by summation xi square. So that is the variance of beta 2 hat comes in, which is basically the expression of variance of an estimated model or variance of the estimated slope coefficient. So in this particular derivation, in the very beginning we started with variance of beta 2 hat, which is sigma square by summation xi square, and that is what we are required to prove. And for that purpose, we started with the original expression of beta 2 hat, where we write summation of ki yi, as we have already done during the unbiasedness step. Then accordingly, we have simplified this expression, and after the simplification, we ended up with wy xi, which we don't want to keep up because it is 1. So it boils down to variance of beta 2 hat, where variance of wy yi, as it is coming up as the final term. And after that, we are left with this expression which says sigma square summation of uy square. So whenever I am writing sigma square summation of uy square, I am basically decomposing the expression of wy in such a manner that it takes the form of a plus b whole square, so that we can get a square plus b square as separate components, and the 2ab component boils down to 0 because the error terms are not correlated with each other. Due to the assumption of zero autocorrelation, the cross term does not exist. So we boil down to the final step, which is variance of beta 2 hat comes up as sigma square, or which is actually constant in the numerator, by summation of xi square. So sigma square divided by summation of xi square comes up as the variance of beta 2 hat, which appears to be the variance of this. So when we go back to the major statement of the Gauss-Markov theorem, we say that beta 1 hat or beta 2 hat, whatever is the estimator, should have the minimum variance property, and that is what the beta 2 hat comes up. And that is what we mean by the blue property. So by blue property, we mean base linear unbiased estimator. So to have the minimum variance, it should be having the property of unbiasedness and linearity. And for minimum variance, the sigma square by summation of xi square should be the minimum variance among all the set of estimators that are being considered. So this is how the property of the estimators basically is dealt with, where a researcher should be very much concerned about the 4 important properties. One is linearity, one is unbiasedness, minimum variance, and for the large sample property, as the number of observations is on the rise, then the variance will boil down to 0. So this is how the entire property of the estimators is being considered. And formally, it goes with the statement of Gauss-Markov theorem. So this calls for the properties of estimators, which are unbiasedness, linearity, minimum variance under the small sample, and for large sample we have asymptotic unbiasedness and consistency. And these properties are very vital for accurate inference and other conclusions to be drawn.